Swayam Prabha. Digital India. Educated India.
Well, I welcome you all to the lecture 3 of week 5. In this lecture, we will be studying various techniques associated with the signal conversion. So, let us begin. The outline of this lecture is as follows. At start of the lecture, we will see the importance of signal conversion, why it is needed, various components associated with the signal conversion devices, and these are comparators and encoders. In a typical mechatronics based system, we need to convert the analog signals into digital format, or we have to convert the digital signals into analog format. So, where we need to convert the analog to digital and where we need to convert digital to analog format, that we will see in details in this lecture, and what are the various techniques that we will see. In our previous class, we have seen various signal conditioning operation. In this lecture, we are studying the signal conversion operations. Any automated system is being controlled by a computer. The computer has microprocessor. The computers are working basically on the microprocessor technology. So the microprocessor is able to process the digital data, but we are getting the analog data from the sensors. So variety of sensors, variety of signal modulating blocks we are using in the automated systems. We need to convert the analog signals into the digital form. The microprocessors are generating the digital signals, and that digital signals need to further convert into the analog form, which can be utilized to actuate the actuators. In automated systems, especially, we need to actuate the drives. It may be the electrical drives or pneumatic drives or the hydraulic drives. Therefore, it is very essential for us to understand the fundamentals of analog to digital converter and the digital to analog converter. So in this lecture, we will be studying some of the basic concepts of the signal conversion devices. So as I mentioned, the components are ADCs, that is analog to digital converter, and the DACs. The other components which are needed to build a DAC or ADC are comparators and encoders. Comparators and the encoders which are needed to build the DACs and ADCs. Now let us see what is the meaning of a comparator. Comparator is an electronic decision making circuit. As the name suggests, the device is comparing the input voltage, or it is comparing the input current at its two terminals, and it just produces a digital signal in the form of zeros or one. Basically, it compares the input voltages and it gives the result that which is the higher one. The comparator has a combination of the semiconductor device, that is diode, and an operational amplifier. The operational amplifier should have the high gain. A typical voltage comparator is essentially a 1-bit analog to digital converter. The meaning is that a simple voltage comparator will take the input at its input terminals and will generate the analog signal into 1-bit digital signal. So let us see how the comparator works. So as I mentioned, the comparator has an operational amplifier. It has two input terminals. This is non-inverting and this is the inverting terminal. The operational amplifier has the output terminal VO. So this is the V out or VO, and we are having the input voltage V in. So the supply voltage is also given. Consider a supply voltage is given of 10 volts and the other terminal of the supply voltage is grounded. Now what the comparator does, it compares the voltages which are applied at these two terminals and it gives the output. If I am applying 1 volt at the positive input terminal that we call the non-inverting terminal and zero point 0.5 volts at the inverting terminal, the comparator compares these two values. If V in, if we consider these as the V in, the input value at the non-inverting terminal is more than the input value at the inverting terminal, then the output will be the 10 volts. The output is nothing but the supply voltage that we applied. So if in this case the voltage at non-inverting terminal is more than the inverting terminal, then it is leading to the output as 10 volts. So the comparison is based upon the values that we are entering at the input terminals. So if I fix this value, if I fix one of the input value as the reference voltage, I'm not changing this, I will keep it constant, then whatever the input voltage we are getting from the sensors or the signal modulating devices, the op-amp will just compare the input voltage with the reference voltage and accordingly it will produce the amplified output. So if the input is say 0.3 volts, 0.3 volts is less than the reference voltage 0.5, the op-amp will generate the signal 0 volt. So the 10 volts would be considered digitally as 1 and the 0 volt will be considered digitally as 0. So if we consider the inverting terminal as the reference voltage with certain fixed voltage value, and if we apply the input if we apply the values which are coming from the sensors or the signal modulating blocks at the non-inverting terminal continuously, then we can generate the outputs accordingly. So if the input is more than the reference voltage, we are getting the signal 1, and if the input is less than the reference voltage, we are getting the signal 0. So if we combine such comparators together, then we can generate the signal in multiple bits. The same thing has been summarized over here. The comparators are comparing the inputs and they are generating the digital output. So as we have seen in our previous slide, a 1 bit comparator is generating 1 bit digital output. But the outputs which are coming out, or the outputs which are given by the comparators, though they are in the form of zeros and ones, but we cannot call them as the binary output. The microprocessor essentially required to have the binary output which is having certain meaning. So a sequence of zeros and ones, no voltage and the positive voltage, we need to convert that into a binary form. So a digital circuit which is carrying out this function is called as the encoder. A simple encoder is the device that converts 2 to the power n input lines into n number of output lines. So these n output lines are following the binary algebra. So let us see how this principle of operation works. To understand this concept, let us look at a typical arrangement of 4 to 2-bit binary encoder. Here we are having 4 input data lines D0, D1, D2 and D3. These input data lines are nothing but the output of the comparator. So we are having 4 comparators attached here: comparator 0, comparator 1, comparator 2, comparator 3. These comparators are op-amp based comparators. As we have seen, based upon the input voltage given to the operational amplifiers and based upon the reference values of the operational amplifiers, the operational amplifiers are giving us certain output. That output at C0 will be utilized to generate the input data line D0. Similarly for D1, D2 and D3. So when 4 input data lines are there, we will be having 2 output data lines. So 2 to the power n is equal to 4. So 4 input lines are giving 2 output lines. To have this type of binary encoder, we have to generate a truth table. We have to use the logic operations to get the required output. A truth table is there on your screen. So we have an arrangement where D0, D1, D2 and D3 are written from right to left, and Q0 and Q1 outputs are written from right to the left. If we say that the comparator output or the data input line D0 is a positive, is 1, then the output at both the data lines would be 0, 0. If the data input line is 1, it's positive voltage, then we are saying that the output line is 1 at Q0 and the output line would be 0 at Q1. For D2, the Q1 is 1, Q0 is 0. For D3, Q1 is 1 and Q0 is also 1. But in case all the input data lines are giving us no data, 0 volts, so that would be that invalid output we will be getting. But let us consider the case when we are having two data lines are giving positive input. If suppose the D1 and D2 both are giving us the positive input, then what will happen? Then the output Q1 and Q0 will also give the result as 1, 1, which is clashing, which is same as the D3 line, D3 input line. So for D1 is equal to 1, D2 is equal to 1, Q1 and Q0 would be 1, 1. The same would be there for the D3. It is a clashing, and that creates the confusion, and that is the major drawback of 422-bit binary encoder. So how to solve this problem? To solve this problem, we have to prioritize the input data lines, and based on the priority, we can generate the output. How this works, that we will see in the next slide. The drawback associated with 4-bit binary encoder can be solved by applying priority to the input data lines. How this priority encoding works, that we will see by taking an example. So in this case, we are taking 823-bit priority encoder. You just note the output data lines that we required are 3. So when we want output data lines equal to 3, what should be the number of input data lines are required? So as we have seen in our previous slide, if the number of outputs are n, so to have n output data lines, we should have 2 raised to n input data lines. So in this case, the output data lines are 3. Therefore, the input data lines would be 2 raised to 3, and that is 8. Thus, we have to have 8 input data lines to get 3 output data lines. Well, we apply the same methodology as we applied for 4-bit. We have to develop a truth table for this. Before getting the truth table, let us arrange the input data lines as seen on your screen. Again, we are arranging the input data lines as D0 to D7 from right to left, and the output data lines as Q0 to Q2 from right to left. Well, here we are providing the priority level to each data line. The lowest priority is given to the D0 data line, and the highest priority is given to the D7 data line. So what is the meaning of this priority that we will see? Now let us see one example to understand the concept of the priority. Look at the row number 2. Here the data input line 1, it showing the high level input value. The comparator is giving high level input value at D1, that is a positive. There is a comparator at D0 as well, but we are ignoring the input value at D0. That means we are giving priority to D1, although we may have certain high input at D0. The meaning is that if we are having D0 as 1, but we don't use that value, we are just simply ignoring. We are simply ignoring the presence of any signal at D0. So thus, for this row number 2, the priority is given to D1. If in certain case the data line 4 is showing the high level input, that is 1, then though there are input data lines, though there are high input at D3, D2, D1, D0, all these would be neglected. They would be crossed. We are not considering them for the conversion application. But in case the D6 is showing the positive level, the high level, then we are ignoring the D5, D4. So in this way, we are prioritizing the input data lines, and when we give the priority to that input data lines, we are ignoring all the input data lines which are lower to that data line. If D6 is having the priority, then the all other input data lines will be ignored. So based on this, we develop this input table, and for each and every row we will be having the output by using the logic gates. So we have to develop the logic gates and OR gates. If D1 to D7 are showing low level input and only D0 is showing high level input, that is 1, then the logic gates based circuitry will give the output as 0, 0, 0. In the next case, the logic circuitry will produce the signal as 0, 0, 1. At the output data line Q0, it will produce high level output, that is 1. If D1 is giving the high level input, and from D2 to D7 we are applying low level input, the encoder will not consider the input at D0. The same logic will be applied, the same methodology will be applied for all other cases, and accordingly we are getting the output based upon the logic gate operations. For example, look at 6th row. In the 6th row, the data line D5 is having high level input. So as per our rule, D4, D3, D2, D1 and D0 will be ignored. If D6 and D7 are having 0 or the low level input, then the logic gate will generate the signal as 1 at Q2, 0 at Q1 and 1 at Q0. So in this way we can say that the output is corresponding to the currently active input which has the highest priority. So what I'm saying, the output corresponding to the currently active input. So in this case, the currently active input is D4. So this row, the currently active input is D4 and it has the highest priority for this row. So accordingly, we are getting the output as 100. If the comparator corresponding to either D7, D6 or D5 is also showing the high level input value, then this would be ignored and the output would be changed. So in this way, the priority level of the input data lines is giving the output, is influencing the output, and thus we are converting the input as the analog signal, that is a continuous function of the time, into the digital output, that is zeros and one. So to convert the analog signal, we are taking help of the operational amplifiers, and then we are converting them into the high level signals and low level signals using comparators, and comparators in association with the encoding device, encoding circuitry, we are generating the digital outputs. Analog to digital converters can be seen on your screen. These are direct conversion ADC or flash ADC, successive approximation ADC, ramp compare ADC, Wilkinson ADC, integrating ADC, delta encoded ADC, and many more. In this lecture, we will look at the direct conversion ADC, its constructional details, and the working principle. On your screen, you can see the electric circuit of the direct conversion ADC or the flash ADC. It is called as flash ADC, flash analog to digital converter, because it is very fast. This type of ADCs have three elements: set of comparators, set of registers, and the encoder logic circuitry. To understand the construction and working of a typical ADC, let us consider that we want to have a conversion of a signal maximum up to 10 volts into the digital binary output format. So we want to convert maximum 10 volts into the digital output binary format, which will be useful for the microprocessor. How it is possible? So for that purpose, we are using 8 to 3 priority encoder. So the 8 to 3 priority encoder we have seen in our previous slides. To have the 3 output data lines, we need to have around 8 input data connections, 8 input data lines. So number of outputs required are 3. Therefore, we are computing the number of comparators are 2 raised to n minus 1, that is 7. And the number of register values are 8. Number of reference voltages are 8. So here you can see the number of reference voltages are 1, 2, 3, 4, 5, 6, 7, and 10. Now, how exactly this ADC works? So to understand its working principle, let us see what will happen if we want to convert the analog signal of 2.5 volts into its binary digital output. So here the 7 comparators which are having the op amp as the basic units are joined in the fashion shown on the screen. You can see at the inverting input terminal, analog inputs are attached. The analog inputs are given at the inverting terminals. The non-inverting terminal is attached to the reference voltage. And how these reference voltages are computing? These reference voltages are computing based upon the final voltage that we want, that is a 10 volts. So it is decided that the first comparator will have the reference voltage of 1 volt, the second will have the 2 volts. There is increment of 1 voltage from the first comparator to the second comparator. Then there is an increment of 1 volt and we are making it 3 volts, then 4 volts, 5, 6, 7, and at the last it would be increased by 3 to have the maximum value of 10 voltage for the conversion. Now to have the increment of 1 volt, 1 volt as a reference volt, we are attaching 1 kilo ohm resistance value for each comparator except the last comparator. At the last comparator, we are attaching 3 kilo ohm as a resistor value. The reference voltages are attached to the non-inverting terminal and the analog input will be given to the inverting terminal. Now let us see how exactly ADC is converting the analog input into the digital binary output. We are applying the analog input 2.5 volt. The input is applied to the first comparator. Here the reference voltage is 1 volt. We are applying the analog input to the inverting terminal of comparator 1 here, that is 2.5 volts. 2.5 volts is more than 1 volt. So the output from the comparator 1 would be of high level, that is 1. Now the input will be passed to the second comparator. So 2.5 volt will be given to the second comparator. At the inverting terminal of the second comparator, the input will be given, that is a 2.5 volt. Its reference voltage is 2 volt. So 2.5 volt is more than the reference voltage 2 volt. Then here as well we are getting the output as high level 1. So this comparator is giving output 1. This comparator is also giving the output 1. Now we are going for the third comparator. The 2.5 volt is further applied to the third comparator here. Its reference voltage is 3 volt. We are inputting 2.5 volts over here. Now the input voltage at inverting terminal is less than the reference voltage 3 volts. Since it is less than the reference voltage, the output at the third comparator would be 0. At fourth it would be 0, then so on and so forth. All other comparators, the output would be 0. Now here we are getting one high level output at second comparator and high level output at first level comparator. As I mentioned, we are using 823 priority encoder. So this comparator we are setting at the least priority and the upper comparators are we are sitting at the highest priority. Since the lowermost comparator is having the least priority, the next comparator to the lowermost comparator, that is a comparator number 2, which is having the high level, that would be considered, and the high output at comparator number 1 will be ignored, as we have seen in the priority encoder in our previous slide. So after giving the input to all the comparators, we are getting the output in this format: 0 0 0 0 0 1 1. This 1 belongs to the comparator number 1, and the rest of the comparators are showing 0 output. Now if we apply the principle of the priority encoder, we are considering the effect of this location only. The first location, the effect of first location will not be considered. Accordingly, the encoder logic circuitry will convert the signal into the digital output signal based upon the truth table that we have seen in our previous slides. So what we have seen in our previous slide, if D2 is 1, then we are getting the output as 0 1 0. The same can be seen here. Based upon the truth table, the binary output is 0 1 0. This binary output will be sent to the microprocessor for its further application. In a similar way, you can solve a problem by considering voltage of 6.8. Let us consider this. So 6.8, the analog input is applied. At comparator number 1, we are getting 1. It will be further compared at comparator number 2. Output is 1. Here the output is 1. Here as well the output is 1, because 6.8 is more than 4 volts. Here again the output would be 1. Here as well we are getting the output is equal to 1. But at this juncture we are not getting any output, it would be 0. So D1, D2, D3, D4, D5 and D6. So here the sixth comparator is giving you the high level output, that is 1. So for that purpose, if you go back to the truth table, the D6 is 1. So if the D6 is 1, if D6 is giving high level output, then the effects at D5 to D0 would be ignored. So in this case, what we are getting in this case we are getting the output as 1 1 0, binary digital output for voltage equal to 6.8 volts. So in this way, we can easily and simply convert the analog signals into the digital binary signals. Now let us see how we can convert the digital signals into the analog format. As we have seen that the microprocessors are generating the signals into digital binary format, but the actuators need the signals in terms of the analog format. To convert the digital signals into analog format, there are a variety of devices, variety of configurations available. Some of the configurations are listed and they are on your screen. The first one is binary weighted digital to analog converter, pulse width modulator, oversampling DACs or interpolating DACs, switched register DAC, switched current source DAC, so on and so forth. Out of all these, we have already seen the pulse width modulator in our previous lecture. In this lecture, we will be studying the binary weighted DAC, how it is useful to convert the digital signals into its equivalent analog output signal. The electronic circuitry for digital to analog converter, that is the binary weighted based digital to analog converter, is seen on your screen. It is called as binary weighted because we are getting the output in terms of an expression of binary weights. The basic element of this converter is an operational amplifier. The operational amplifier has the output voltage terminal, and there are two input terminals. We are taking the feedback from the output and we are attaching that feedback to, or we are giving that feedback to the inverting input terminal. So this operational amplifier we are using in inverting mode. The function of the inverting mode operational amplifier already we have studied in our previous lecture. So in the path of feedback, we are attaching a reference resistor to the non-inverting input terminal. The reference voltage is attached. At the inverting terminal, we are applying the input. The input is in the form of binary number. The binary number will have the bits. Here we are considering a binary input with 4 bits. So we are applying the digital input, something like this. So in this case, the most significant bit is 1. Then we are having 1 to the next bit, 0 to the next one, and the least significant bit is 0. So this binary input is given to the inverting terminal through a series of registers. The values of these registers are shown. The most significant bit is attached with register value of R. The next one who is having less significance than the most significant one will have a register value of twice of the R, twice of the resistance of the MSB. The third one will be having the increase in resistance, that is 4 times of the resistance of the MSB, and the least significant bit will have the maximum resistance attached, that is 8 times of the resistor value. So if you notice that most significant bit is attached to the least resistance value, while the least significant bit is attached to the most resistance value. Why we are doing this, that we will see. Now let us see how this binary weighted DAC is working. Now if I take the example as 1 1 0 0 as the binary input, when the MSB value is 1, that is high level input, then voltage belongs to the MSB will be the reference voltage. So if I say V1 is the voltage associated with MSB with resistor R, V2 is associated with the resistor 2R, V3 is associated with the resistor 4R, and V4 is associated with the LSB with 8R. So if the value of MSB is 1, that means the voltage 1 will be the reference voltage. If the value of the second bit is 1, then the voltage of V2 would be the reference voltage. And that reference voltage will be amplified based upon the correlation of the reference resistor and the input resistor. Then we can say that if V1 be the input voltage at MSB, most significant bit, V2 be the voltage at the next bit, and so on, then for the 4-bit DAC we can write V1 divided by R plus V2 divided by twice R plus V3 divided by 4 times of R plus V4 divided by 8 times of R is equal to V out divided by R. Here we can notice that we are dividing the V1, which is associated with the MSB most significant bit, with least resistance. That means we are giving more importance, more priority to the most significant bit. On the other hand, if you notice here, V4 is associated with the least significant bit, but it has been divided by the maximum resistance value. That means we are trying to reduce the influence of the least significant bit in the conversion of the binary signal into the analog value. Now, as I mentioned, V1, V2, V3, V4 will have the reference voltage value if the digital input is 1, or otherwise it will be 0. V1, V2, V3, V4 will have the reference value voltage if the input is 1, otherwise it will be 0. Hence we can say that the output voltage is proportional to the binary conversion of the input values of the voltages at the bits of the input. So I can write V out is directly proportional to 2 raised to power 3 into V1, 2 raised to power plus 2 raised to power 2 into V2 plus 2 raised to power 1 into V3 plus 2 raised to power 0 into V4. V1, V2, V3, V4 will be the reference values if that corresponding bits are giving us the digital input of 1. Why I'm writing here the proportional? Because the actual values will be dependent upon the gain of the operational amplifier, and the gain is dependent upon the value of reference register and the value of the input registers. So when we choose the appropriate values of input registers and reference registers, accordingly we can precisely compute the value of the output voltage based upon the signal given in terms of the digital input. In this way, we can easily convert the digital signals into the analog value, and that analog value will be given to the actuators to carry out the desired purpose, that is actuation of the devices. So with this, I would like to stop for this lecture. Let us summarize the lecture 3. In this lecture, we have seen the signal conversion, its need and application in the development of mechatronics based systems, various components of a typical signal converging device such as comparators and encoders. We have seen how they do work and what are their applications. Then we saw how to convert analog to digital form of the signals and how to convert the digital format into the analog format. So, for that purpose, what are the various techniques that we have seen, and at preliminary we have discussed 2 techniques. In lecture 4 of week 5, we will be studying the microprocessor technology, that is the brain of a mechatronics based automated system. The definition of a microprocessor system, its architecture, it has variety of elements. We will see the functions of all the elements. Then we will study the meaning of a microcontroller, how the microcontroller is different than the microprocessor, what is the meaning of a microcomputer, and at the end we will see the PLCs, that is programmable logic controllers, which are often used in automation industry.